My name is Catherine Canatella, and this is my constant velocity motion lab. A rolling spray bottle at constant velocity where assumed Fnet equals 0 was observed, and it was discovered that the computational model provides a good prediction for the motion of the observed model. Here you can see the observed model. The first frame was set after the hand pushed the bottle. The last frame was set before the bottle rolled off the table, which allowed me to assume constant velocity. I chose the positive x-axis so the bottle moves along it at constant velocity. The origin is set at the hand. I used the center of the bottle as the average position and used a ruler to calibrate the video and set that as the length scale for the videos at 0.32 meters. As I can see from the tracker data, the time between frames is 0.033 seconds and the total time is 0.833 seconds. I then graph the data from tracker in a position versus time graph. As you can see, the slope for the line is relatively constant with an R-square value of 0.9988. This shows that the bottle was moving at constant velocity. Here you can see the computational model. To predict the motion, I needed the mass of the bottle, which was calculated at 0.226 kilograms. To get the initial position, I analyzed the first frame of the video and discovered that it was 0.018 meters. V initial was estimated by taking the change in position over the entire video clip, which was the final position minus the initial position, and dividing it by the total time. Delta t is given in the video clip at 0.033 seconds. I predicted the new velocity by starting at t equals 0 up until t is less than 0.833 seconds. Because that's how long my video was, and applied Newton's second law. Here, since the object is moving at constant velocity, v final equals v initial. This means that the second term of Newton's second law will be 0. The second term is Fnet over m delta t. Since neither m nor delta t is 0, we must assume that Fnet is 0. So, I set Fnet equal to 0 in my computational model and used that to predict the motion. I'm now going to run the module to show you the visualization of the computational model. As you can see, the origin is located here. The ball moves to the right in the positive x direction. It starts slightly to the right of the origin and gets more positive as t increases. A good way to compare the computational model and the experimental model is by graphing them on the same graph. The red squares represent the computational model, while the blue diamonds represent the experimental model. As you can see, they are relatively close, which means one can conclude that the computational model is a good way to predict the motion of an object. Newton's second law, v final equals v initial plus Fnet over m delta t, allowed us to accurately predict the motion of an object moving at constant velocity in the real world. The first discussion question is, what if we change the origin? The initial and final positions will change, however, this will not affect the velocity because the difference between the initial and final positions will be the same as before. For example, if we move the origin to the right 1 unit, giving the initial position a larger value, then 1 unit would be added to the final position as well. This means that the change of position would still be the same, and the velocity would not change. The second discussion question asks if it is possible to say the number of pushes and pulls used to give the net force of 0. No, we cannot predict the amount of pushes and pulls. However, we do know that the object is moving at constant velocity over a period of time and that it does have a mass. As you can see from the equation below, that we need the second term to cancel out so that v final equals v initial. Therefore, Fnet must equal 0 because we know that m does not equal 0 and delta t does not equal 0. Therefore, we can assume that Fnet equals 0, which means that we can also assume that the pushes and pulls cancel each other's forces.